In this example problem, we're going to find the stress-strain relationship for confined concrete for the given section. We're going to look at our compression only, and we'll use the Mander et al. 1988 stress-strain relationship to make a reasonable estimate. So here's our section. You can see we have 3 number 8 bars in both compression and tension. We have number 4 grade 60 rebar spaced at 4 inches and a 2-inch clear cover. You can see also our section is 18 inches by 24 inches. So the first thing that we need to do is we need to determine the lateral stress or restraining stress. For our rectangular reinforcement, we can determine our lateral restraining stress using our F sub R1 and F sub R2. For our section, we have our FR1 equal to 2 times the area of our number 4 bar, so 0.2 square inches, times Fy of our number 4's, 60 KSI. We'll divide by our spacing, which is 4 inches, and then our DC value, which our DC in this case is 18 inches minus 2 times 2 inches cover minus a 1/2 inch, which is the diameter of our number 4 bar. So this will be the distance between center to center of our stirrups. So we'll find our FR1 to then be 0.44 KSI. We can do the same thing then for FR2, which in this case is on our 24-inch side. So we'll use our D sub C value as the center to center from our on the 24-inch side. So you can see that's the only real difference between the two, since we have our number 4 bars on all 4 faces of our section. So the next step will be to determine the ineffective area. We can find our ineffective area using the equation shown with a W sub I prime value. So in our case, we have our W sub I prime being the inside to inside here. And so we'll have 17 inches on one side, and inside to inside on this other side will be 11 inches. So in our case, it's fairly simple because we don't have any cross ties. If we had a cross tie in either direction with another layer of reinforcement, then this value could decrease. But in our case, we'll just have our A ineffective then equal to 17 squared plus 17 squared plus 11 squared plus 11 squared, all divided by 6. So that'll give us an A ineffective of 136.7 inches squared. So using our ineffective area, we can next determine our effective area. We can determine our effective area using the expression shown here. So we found BC and DC previously, and we also found our A ineffective previously. So we can just know our A effective is then 19.5 inches times 13.5 inches minus our A ineffective 136.7 inches squared, and then times our 1 minus our S prime, which our S prime is from inside to inside of our reinforcement, so we have 3.5 inches instead of 4 here, over 2 times 19.5 times 1 minus 3.5 over 2 times 13.5. And we'll find that our A effective will be 100 square inches. We next need to calculate our efficiency factor. So in order to do that, we need to find our A sub cc. So we can find our efficiency factor first by finding A sub cc, and we'll find that our area of our confined core is going to be our BC times DC, so 13.5 times 19.5 minus our total area of our steel. So we have 6 number 8 bars, and this will give us a total confined area of 258.5 square inches. Our efficiency factor is then just our effective area over our confined area. So we'll have 100 square inches divided by our 258.5 square inches to find our final K value of 0.387. So we can use this now to determine our effective lateral restraining stresses. So our effective lateral restraining stresses are just going to be our efficiency factor times the stresses that we found before. So in our case, our FR1 is going to be our restraining stress, or sorry, our efficiency factor, so 0.387 times our FR1, which we found to be 0.44 KSI. And similarly, our FR2, 0.387 times our FR2, which was 0.31 KSI. So we'll find our effective stresses here to be 0.17 and 0.12. We next need to normalize both of our FR1 effective and FR2 effective by our concrete compressive strength so that we can enter into the plot by Mander. So we'll have our normalized stress here being 0.17 KSI divided by our F prime C, which we were given as 4 KSI. And then we'll find this to be 0.43, or sorry, 0.043, and then our 0.12 KSI normalized by 4 KSI, which will give us 0.030. We can then use these values to enter into our plot. So first we'll have 0.043 as our larger confining stress. So we'll enter in right about here. And then we have the smaller, we have 0.03. So we'll enter in right about here. So if we follow this up, and we follow this over, see we intersect right about here, so then we can back out our confined strength ratio. So I assumed here that our confined strength ratio, so our F prime CC equaled 1.22 times F prime C. So we're getting a 22% increase in our strength with confinement. So in our case, we'll have 1.22 times our 4 KSI, and we'll find our F prime CC to equal 4.88 KSI. So next we can determine the peak strain, and we'll figure out all of the values needed for our plotting. So we'll continue using Mander's expression, so we can use this expression for the strain at peak stress, and plugging in our values, we'll have our epsilon naught as 0.002, 1 plus 5 times 4.88 over 4 KSI minus 1, and we can find our epsilon CC then to equal 0.0042. So next we can determine the maximum strain. We'll determine our maximum strain using this expression here, which involves a rho sub s, which is our reinforcement ratio, which accounting for the volume of hoops divided by the volume of our confined concrete. So in our case, the total volume of our hoops, and this is on one plane, so we'll say is 2 times 0.2 inches squared, since we have 2 legs in both the top and the bottom, and then we'll have the total length of these bars to give us a volume. So 13.5 inches plus 19.5 inches. Now we need to divide by the volume of our confined concrete, which in our case is 13.5 inches times 19.5 inches times 4-inch spacing in between the bars, in between our transverse reinforcement. So we'll find our rho sub s to be 0.012. We can then plug our rho sub s and our other knowns into our EC max expression, and we'll find that our EC max, or epsilon C max, is equal to 0.004 plus 0.1 times 0.012 times our Fy, which is 60 KSI, divided by our F prime C, which is 4 KSI. This is, note it's not our confined compressive strength, and we can find that our maximum value then is 0.022. So finally we need to determine our last required coefficients, specifically this R coefficient. So our R will require our modulus of elasticity, which you can see I found to the right here, just using the simple ACI expression. So then we can plug in and find our R value. So make sure that you use consistent units for this value. So we'll have 3,605 KSI divided by 3605 KSI minus our F prime CC, which in our case is 4.88 KSI divided by our epsilon sub CC, which we found to be 0.0042. 1.42. So we'll then find our R value to be equal to 1.48. So now we have all the values for plotting. So the two expressions that we can plot then are shown here for FC and this X value. So ultimately we want to plot our stress versus strain. So this is just a stress strain plot where we have X here. So let's plug in all the rest of our values. So we'll have 4.88 KSI for our F prime CC. We'll keep X in terms of X, and then we'll have our R was 1.48. Then we have it divided by 1.48 minus 1 plus our X to the 1.48 power. And our X then is just equal to epsilon C, which we're plotting against, divided by 0.0042. And we can then plot these two equations, or this equation, and get the plot shown here in the bottom right. And I just did this using Excel, or you can use any kind of spreadsheet software.